after all, you are allowed to use your graphing calculator. So let's take a look. When I graph this first, so this is x squared minus 4x plus 13. So x squared minus 4x plus 13. So there it is. Do we have any x-intercepts? No. So right away, this tells us that when I factor this thing, the factors themselves will have imaginary numbers inside. Because the factors, if you wrote out all your parentheses, if there were real numbers inside, then that would be an x-intercept. But there is no x-intercept, so when I factor it, there can't possibly be real numbers in there. Because if there were real numbers, there would be actual x-intercepts. But there are no x-intercepts, so we know that when we factor it, it's going to be imaginary numbers inside our factors. So let's go ahead and give it a shot. Fortunately, with a just simple quadratic, we don't have to do any synthetic division at all. It's just the quadratic formula. So let's go ahead and do that. Number 11. Go ahead and let's just identify that we have a is equal to 1, b is equal to -4, and c is equal to 13. And when we do the quadratic formula, we get x equals -b plus or minus the square root of b squared minus 4ac all over 2a. So we'll plug everything in, so -b, b, a, c, and a. So we go through and start reducing all of this. -4 is +4 plus or minus the square root of 16 minus 52. Well, what is 16 minus 52? 16 is, yes, -36 all over 2. So right away, we see the square root of a negative number, and that's not real. And originally that would mean we'd say, oh, that's imaginary. And since it's imaginary, we would know that this particular quadratic, we should already know this, is floating above the axis, right? So that's true. We already know that. We looked at the graph. As soon as we see a negative number there, this number is imaginary, therefore there are no x-intercepts, and therefore it's floating above the axis. Well, let's finish the problem. What's the square root of -36?
-1 squared times 6.
Well, let's remember our process. We split that apart into 36 times -1. And then we can split that into root 36 root -1. And the square root of 36 is just 6, and the square root of -1 is just I. So we have 6i. So here we have now 4 plus or minus 6i, all over 2. And then that we can further simplify because 2 goes into 4, 2 goes into 6. So now we can say 2 goes into 4 twice, 2 goes into 6 3 times, and we have now 2 plus or minus 3i. And let's take that one step further and say that our x-intercepts, air quotes here, are x-intercepts because they aren't really x-intercepts. Our solutions are 2 plus 3i and 2 minus 3i. Notice that those are conjugates, right? So the 2 x-intercepts that we found are conjugates. And so now the question is, how do we put this into our factored form? Just keep in mind here, if we had had a normal quadratic with x-intercepts, like let's say that it was x squared plus 7x plus 12, that would have factored into x plus 3, x plus 4. And furthermore, that would tell us that the x-intercepts are x equals -3 and -4. So let's remind ourselves, how do you take the actual x-intercepts and put them inside of our factored form? You take your x-intercepts and you start by writing x minus x minus. Okay? That's how you set up a polynomial, a factored polynomial. And then what you do is you just drop in your x-intercepts. So I have my original polynomial here. This is just an example. I write it out as a factored form polynomial by writing parenthesis x minus, parenthesis x minus. And then whatever x-intercepts I find, or that is whatever solutions I find from the quadratic formula, I just put them inside. So I put my -3 there, my -4 there. And of course, those are both double negatives. And so they just become positive. And that gives me the factored form that I know it is. All right? So this is just a nice little reminder of how you would do it with a regular normal polynomial. So now what do? We have our polynomial, which was x squared minus 4x plus 13. And we want to factor that into parenthesis, parenthesis, x minus, x minus. And so what do? We just drop those numbers in and simplify. So if I now drop those in, a little bit of simplification happens. I will have x minus 2 plus 3i and x minus 2 minus 3i. And that is the factored form. Honestly, it's probably fine just to leave it like that. But if you really wanted to, distribute that negative sign, which is perfectly valid and fine, then I would end up with x minus 2 minus 3i and x minus 2 plus 3i. Both of those would be perfectly valid. Probably this one's easier, because why take it one step further if you don't have to? So what do you all think? This is now the factorization of this quadratic, which shows what the x-intercepts are. But these are actually just the solutions, the numbers, the mathematical objects that I can plug into that equation and make it true. Now, probably at least once in your life, you should verify that for yourself. You should say to yourself, what is this 2 plus 3i thing? Apparently, it's a mathematical object that has the power to make this equation true. X squared minus 4x plus 13 equals 0. So what do you think? If we plug 2 plus 3i into that thing, will it actually make it true? I mean, it better, because that's what we're claiming, right? That's fundamentally what we're claiming a solution is. A solution is an object that you can plug in to an equation and make it true. So just once, I want to show it to you. If you have that x squared minus 4 times that plus 13, there should be at least a temporary moment of disbelief when you see me put in 2 plus 3i and 2 plus 3i. And you just look at that and you think, is that really going to work itself out to be 0? Does that look like this is going to multiply out to equal 0? Then maybe you have optimistic confidence. You're like, yeah, that'll be 0. Or maybe you're like, no way, look how crazy that is. There's a bunch of i's in there. That's not going to equal 0. So let's try it. If I square out 2 plus 3i, and I'll go ahead and distribute my 4 right now. So that's minus 8, and then that's minus 12i, and then that's plus 13. Okay, we got a real mess here. So now I'm going to FOIL that. So first, 2 times 2 is 4. Outer, 2 plus 3 is 6i. Inner, 3i times 2 is 6i. Last, 3i times 3i is 9i squared. How's it looking? Does that look like it's going to simplify down to be 0?
Yeah.
We hope. So what can I do? I can combine my like terms here. So I have 4 plus 12i. What's I squared again? Negative 1, so that's really minus 9. Minus 8 minus 12i plus 13. Now I want you to see something. In mathematics, this is almost always true. It gets worse before it gets better. So what we were just doing was the part of it getting worse, right? So all of this right here was gets worse. And you should just know that about algebra. That when you're doing an algebra problem and you start it, you're like, okay, I'm starting the problem. And then you're like, oh, it's getting worse. That's normal. That's a normal experience because now it's about to get better. What happens? The 12 i's cancel out. And then let's just start adding. So I've got 2 positive numbers. 4 plus 13 is 17. And then I've got 2 negative numbers. Negative 9 minus 8 is minus 17. And 17 minus 17 is? Oh my goodness. All right, so it's worth seeing at least once. And you should go home and try that again on your own to really appreciate that this thing, 2 plus 3i, is a valid mathematical object that has the power to make this equation true. And if I now replace 2 plus 3i with 2 minus 3i, that would also make this thing turn into 0 equals 0. All right? Because at some point, this all feels so hand-wavy to say, the answer is 2 plus 3i. And this is the factored form. Like, you might feel like, what are we even talking about? Is this just a bunch of focus? But no, in fact, when you really plug it in, it really boils down to 0 equals 0, which is a basic true statement. How do y'all feel about this? Karis, how you feeling? Is that all right? Syra, what do you think? That's okay? Erica? Huh? Guadalupe? Any questions? Joseph? All right. Jessica? All right. All right, well, so we did it. We did the first one. Now you might be looking at that and saying, oh my goodness, how much of that do I have to do? Well, I mean, this whole last part that I just did here, that was just verification. Right? I just verified that the answer I came up with really did what I claimed it would do. And then this was the actual work that needs to be done, which is to do the quadratic formula, and that will generate your imaginary solutions. We are going to basically always get our imaginary solutions by doing the quadratic formula. All right. All right, well, that was number 11. Let's try. Now, I'm going to choose which ones to do here strategically. So let's take a look at, we're going to graph them first. Let's take a look at number 12. X cubed minus 2x squared plus 9x minus 18. All right. Well, take a look at this. How many x-intercepts do we have? 1. In fact, the graph is pretty unexciting, right? It just kind of goes up, goes to the right a little bit, then it keeps going up. And so there's 1 x-intercept at 2. But the fact is, this was a cubic. So how many, the maximum number of x-intercepts was 3. There's only 1, but the number of solutions should be 3. We should have 3 solutions. Now, we just went ahead and cheated and found out that the x-intercept was 2, and you all can feel free to do that as well. When you're given a polynomial, you can type it into your graphing calculator, see what the x-intercept is, and then that way, your choice of doing synthetic division becomes much easier. So everyone, let's look at 12 together. We have f of x equals x cubed minus 2x squared plus 9x minus 18. Let's just review from yesterday, and by yesterday I mean Monday, what the rational roots theorem and what Descartes' rule of signs said. Rational roots theorem or rational zeros theorem says to take every divisor of the last number and divide it by every divisor of the first number and make every possible fraction, and those are the only numbers you should bother trying with synthetic division. So what are all the factors of 18? If you're not sure, I would make the factor table and say 1 and 18, 2 and 9, 3 and 6, and is that it? So now write them in order. So my factors are, or my divisors are 1, 2, 3, 6, 9, 18. Over all the divisors of 1, which is just 1. And we look at every possible fraction, plus or minus, and we now know that the only numbers that we should bother trying in synthetic division are 1, 2, 3, 6, 9. So that's our list of candidates. Rational roots theorem gives you a list of candidates. Those are the numbers we should bother trying with synthetic division. Of course, we already know because we looked at the graph. What number should we use? 2. And indeed, that is on our list. We are going to use the number 2. But I just wanted to review the rational roots theorem since we just did it on Monday. Now, what about Descartes' rule of signs? How does that work? Descartes' rule of signs allows us to come up with the number of positive x-intercepts and the number of negative x-intercepts. Again, just candidates. This process is going to tell us potentially how many positive x-intercepts we have and potentially how many negative x-intercepts we have. So let's do the process. Remember, to find p, shouldn't put equal sign. To find p, we look at the signs of the original function. And so what are the signs? Plus, minus, plus, minus. And how many sign changes do we have? Plus to minus is 1 sign change. Minus to plus is another sign change. Plus to minus is another sign change. So our value for p is 3. And then you take that number and you start subtracting 2 from it. So 3 minus 2 is 1. 1 minus 2 is negative 1. Can't have a negative number of x-intercepts, so we're done. That tells us that we either have 3 positive x-intercepts or 1 positive x-intercept. And how many positive x-intercepts do we actually have? 1. So we know that it's this as 1. Okay, now how about n? Remember, to get n, the number of negative x-intercepts, you change the sign on which ones? Which terms do you change the sign on? Just the odd terms. So that's x to the 3 and x to the 1. So now I'm going to write down that's positive, but I'm going to make it negative. That stays negative. That one becomes negative, and that one stays negative. And now we look for the number of times the sign changes. So did it change? No. Did it change? No. Did it change? No. So the number of negative x-intercepts is 1. That's fascinating that Descartes' rule of signs guarantees that for us. And in fact, are there 0 negative x-intercepts? That's correct. There were no negative x-intercepts. So what that tells us then is that Descartes' rule of signs tells us right off the bat, I don't have to look for any negative x-intercepts. So I don't have to consider any of those candidates for the negative value. And I know that I'm either going to find 3 or 1 positive x-intercepts. Now, of course, we're going to look at the graph we know the answers to. So now let's go ahead and do that. let's do synthetic division. We're going to write down our original coefficients, 1, -2, 9, -18. And I'm going to use the number 2, which we know is correct because we looked at the graph. If you didn't look at the graph, you just have to sit there and start trying positive numbers. You try 1, then 2, then 6, then 3, and then 9, and then 18 until you find it. So synthetic division gives us drop the 1, multiply, add, multiply, add, multiply, add. Now we can go ahead and read this information. We started as a cubic, so this will be x squared, x, no x. And I can now write down my factored form as x minus 2 times x squared plus 9. So not bad. This is what we've done so far. So far, we have factored x cubed minus 2x squared plus 9x minus 18 into x minus 2 times x squared plus 9. Guess I'm going to leave that there. I need a little more space. So I'm going to finish it right here. So now what do we do with, we started off with x cubed minus 2x squared plus 9x minus 18. And now we're here, x minus 2, x squared plus 9. We want to continue factoring until we have simple factors all the way across. That needs to be our goal, is that we're going to have 3 simple parentheses with x, 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 minus, minus, minus. That's what we need. We already have the first one. So now how do we get to the next one? So what do we do with x squared plus 9? Yeah, right. By the zero product rule, we're setting each of these things equal to 0. So we have a couple different ways we could do this. You can either factor, solve, or do the quadratic formula. So factor, that won't work. Because the only way we can factor that would be if it had been x squared minus 9, you could have done x plus 3, x minus 3. But that's called the difference of squares. This is not the difference of squares. This is the sum of squares. So we can't use that technique. We could do the quadratic formula. That'd be just fine. The quadratic formula would be a equals 1, b equals 0, c equals 9. And then away you go during the quadratic formula. It'd be negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. And that would give us x equals 0 is just 0, so plus or minus root negative 36 all over 2. We already know what root negative 36 is. That's 6i, so plus or minus 6i all over 2. And that gives us plus or minus 3i. Okay, so I just demonstrated that real quick so you could see that you can do the quadratic formula, and it will give you your 2 different numbers. So again, that means 3i and negative 3i would be the 2 objects that I drop in to my final factored form. I'm about to do that, but let me show you the other solution. Other than doing the quadratic formula, you can also just solve algebraically. Remember, when you do factoring, the whole point is to have something times something times something to use the zero product rule. So you can just set that thing equal to 0 and do the algebra. This might, compared to the quadratic formula here, this is much more straightforward to just move the 9 over. X squared equals negative 9. And then you square root both sides. And what's the square root of negative 9? It's just 3i, right? Because you can pull the negative out as an I, and the square root of 9 is 3. And so I immediately get the answer, plus or minus 3i. So which way was easier, the quadratic formula or just setting it equal to 0? Yeah, but that's only because it was easy. If this was a real quadratic with a b term, you'd have had to do the quadratic formula. Okay? So one way or the other, you either have to do the quadratic formula or you just set it equal to 0 and solve. But we now know that the solutions, which are x-intercepts, are positive 3i and negative 3i. And so you drop those in to the factored form, and you say 3i and negative 3i. And the last thing you would do is just clean up that double negative. So what's our final answer? X minus 2, x minus 3i, and x plus 3i. So now look at what we did. All right? Because this is what you've just spent the last 2 weeks of your life learning about. Right? You were sitting at home thinking to yourself, man, here's a cubic polynomial. I wonder if I can factor that thing. And so now we just did. We factored it. Now looking at this, what can we say about our graph? Right? Let's not forget our end-all, be-all is to be able to make a hand-drawn graph. So the first thing we can say is that it's cubic. So our end behavior should look like this. We also know that my y-intercept is negative 18. So I can come down here to -18 and put a dot. And I also know that I have an x-intercept at 2, so I can put a dot there at 2. And the fact that these are imaginary, tell me what? Yeah, there's no more x-intercepts. They're imaginary. So that's it. That's what I have. So I would put a tail going up to the right, and then that's also my tail going down to the left because there's only one x-intercept. Remember, you always put that tail on the farthest right x-intercept and put this tail on the farthest left x-intercept. There was only one x-intercept, so both tails go to it, and then whoop, that's your graph. All right. Let's try just a couple more, just to round this out. And let's try a much larger polynomial. Let's do one that is bigger than a cubic. Maybe let's do a 4th power or a 5th power. By the way, a 4th power is a quartic, and a 5th power is a quintic. Quartic, much like there are 4 quarts in a gallon, quartic. Okay, so let's see here. The next 2 are cubics. I'd kind of like to do something bigger than that, so you can feel free to cross out 13 and 14. Aha, there we go, 15 and 16. Okay, what did I just say? Did I just say to cross out 9 and 10? I think I did. I'm lost here. Okay. So let's look at 15 and 16, and we'll, again, be strategic about choosing one. Let's graph it first. So 4x to the 4 minus 4x cubed plus 13x squared minus 12x plus 3. All right, there's our graph. What do we see? It touches down just once at a half. Not only that, but is that a bounce or a slice? That's a bounce, so we know that that particular factor of x minus a half should have a power of 2 on it. Not only that, that tells us that we can plug 1/2 into synthetic division twice to produce a 0 in the synthetic division process. So there's our graph. Now notice this was a 4th power, so how many solutions are there? There are 4. There are 4 factors, but since it only touches the axis once, that has a multiplicity of 2, then we'll have 2 imaginary solutions as well. So let's go ahead and do that, folks. We're going to do number 15. Oh, and then somebody remind me, I really do want to do one of those more exercises with you that we haven't seen yet in class. Okay, so everybody, we're going to do number 15. Everybody ready? Ready, pumped? So take a look, write down number 15 in your own hand. F of x equals 4x to the 4th minus 4x cubed plus 13x squared minus 12x plus 3. Now, just a word about rational roots theorem and Descartes' rule of signs. That would be something that you could do at any time. You could do that for every single problem. So right now, I could go ahead and say, by rational roots theorem, the only possible numbers I should bother trying are all the factors of 3, which is 1 and 3, and all the factors of 4, which is 1, 2, and 4, and then every possible fraction, which is going to give me 1 over 1, 1 over 2, 1 over 4, or 3 over 1, 3 over 2, and 3 over 4. So those are the only candidates that I should bother trying with synthetic division. Right? So I just did every possible 1 over 1, 1 over 2, 1 over 4, 3 over 1, 3 over 2, 3 over 4. Those are the only numbers that could potentially work in synthetic division. And in fact, we know the answer because we graphed it. Which one are we going to use? We use 1/2 because we know that that worked. Furthermore, it was positive 1/2, right? So even though the rational roots theorem gives us all those numbers plus or minus as candidates for synthetic division, we know that it's just 1/2. And furthermore, with Descartes' rule of signs, I can go ahead and find the positive number of x-intercepts. This is plus, minus, plus, minus, plus. How many sign changes? 1, 2, 3, 4. Use 4. Or 2 or 0. So I either have 4 positive x-intercepts, 2 positive x-intercepts, or no positive x-intercepts. We already know the answer, that there's a single x-intercept with a multiplicity of 2. So we know that this is the going to be the answer. And if I go ahead and change the signs on the negative powers, so that one's still positive, this one's positive, this one's still positive, that one changes to positive, that one's still positive. How many sign changes are there? None? So there we go. So Descartes just confirmed everything that we already knew by graphing it. We'll have no negative x-intercepts at all. We will either have 4, 2, or 0 positive x-intercepts. We know the answer is 2 because we graphed it. And we know the rational root that we're going to find is 1/2. Okay, so I just did that one more time with you so we could all see how it worked. Now let's go ahead and do the synthetic division. So we write down our coefficients, 4, -4, 13, 12, 3. And we know we're going to try 1/2. Furthermore, we know we're going to do 1/2 twice. Right, we're going to do synthetic division once with 1/2, rewrite our polynomial, then we'll go ahead and do synthetic division again with 1/2, reduce our polynomial, and then we'll finish it off by doing the quadratic formula. So everyone go ahead and do synthetic division. And by the way, folks, this is, this is it for chapter 3. This is the culminating activity. This is the, like, what do you call that? Like the end of a show where, like, they play lots of loud music and flash lights at you to do fireworks. Yeah, finale. Thanks, Joseph. This is like the finale.
I did see it online.
Oh, sure. All right, so let's check from the first synthetic division. Drop to 4. Half is a nice fraction to use because you just think half. So multiply half of 4 is 2, add -2, half of 2 is 1, negative, 13 minus 1 is 12, half of 12 is 6, 6 minus 1 is -6, half of -6 is -3, and sure enough, 0. So let's write down our new factored polynomial. We now know that it's x minus 1/2, and the rest of it is, it started as x to the 4th, so now it's x cubed, x squared, x no x. We have 4x cubed minus 2x squared plus 12x minus 6. Okay, so is everyone to there? If you're beyond that, just wait 1 second and let's look. This is interesting. Look at now my reduced polynomial. Now I'm at a cubic and I need to solve this one. Well, looking at this one, we're basically starting over. We're like, okay, now I need to reduce this polynomial. I need to factor this polynomial. Well, if you look at this polynomial, we would have a brand new set of options from the rational roots theorem. Because now you'd have to say, okay, all the factors of 6 over all the factors of 4. And you'd have to say, oh man, all the factors of 6 over all the factors of 4. We now have even more possibilities to consider in synthetic division. But do we have to bother considering this larger set of possibilities? No, because we already had the original set of possibilities for the first polynomial. So the fact is that even though this polynomial has apparently more possibilities, we only ever have to think about the original set of possibilities, which is kind of nice. Okay, so now, what do we do? We do synthetic division again, once again with a half. So, now by the way, the only reason we know that we can use half twice is because we saw it on the graph, and it was a bounce. So we knew that the exponent had to be a 2 or 4. It could have been x minus 1/2 to the 4th. It just has to be an even power. The fact is, if you didn't see a graph, you would be back to the drawing board with just trying all those numbers again. Right? You'd just be working your way through the list of candidates. It'd be a very time-consuming process. And I'm telling you, as a friend, you don't have to do that on the test or on your homework. You can just use your graph, find the x-intercepts, and then do the process. Okay, so here we go. Let's do it again. 4, -2, 12, -6. We're going to do 1/2 again. And so synthetic division gives us. Okay, good. So let's bring everything down. We get to bring down the x minus 1/2, the new x minus 1/2, and then this reduced polynomial. It was a cubic, so now it's x squared, x no x. And so what do we have so far? X minus 1/2 times x minus 1/2 times 4x squared plus 12. That is what our factored polynomial is so far. So one thought, you use synthetic division to work your way down from a fourth power or a fifth power all the way down to a quadratic. And then at this point, you ditch the synthetic division and just move on with normal quadratic analysis. Okay, so at this point, we wouldn't now proceed to do more synthetic division because look at our options now. You'd have all the divisors of 12 divided by all the divisors of 4. That's even more possibilities. Even though we know that we can just stick with the original list of possibilities, you wouldn't want to continue doing synthetic division. You can now just factor this. So first of all, what can I take out of 4 and 12? You can take out 4, right? So watch carefully how I do this. We bring the 4 all the way up front. So now we say 4 times x minus a half times x minus a half times x squared plus 3. So that's what we have so far. We brought the 4 all the way up front. Is that okay with everybody? Bringing the 4 all the way up front? All the way up front? Well, because for instance, you could have just brought it right there and have that. Right? Would that have been more appropriate?
Well, I guess I'm more curious as to why we always do the zero product. Is that result the same?
Oh, okay. Well, now that's fair. I mean, you just want it right there as you are. Do the zero product rule?
Well, I guess I'm more curious, does the 4 stay? So it would be f of x equals.
Right. See, the 4 has to stay there. The 4 has to be in there somewhere. And if you just did this zero product rule right now, and you had 4x squared plus 12 equals 0, and then you had 4x squared equals negative 12, and then divide up to 4x squared equals negative 3, and then you have x equals the square root of negative 3, which is x equals plus or minus 3i. And if you just now put in x plus 3i and x minus 3i, the 4 would be gone. Yeah, so you need that 4 to be in there somewhere. So thank you for asking the question. Very important, folks. When you get to here, you do have to factor anything out that you can. Like you have to factor out a common number or take out a leading negative before you go and do the actual solving. So yeah, we have to bring that 4 out, leaving behind x squared plus 3. And then you'll notice, now when you do the zero product rule on that last bit, x squared plus 3, you still get the same solution. So I'd have x squared plus 3 equals 0. And so move the 3 over, x squared equals negative 3, square root both sides, x equals plus or minus 3, root 3i. So again, that wasn't 3, it was root 3. So now we're down to this solution, plus or minus root 3i. That means my two solutions are positive root 3i and negative root 3i. So now what do? We have 4 times x minus a half times x minus a half times, and you just write it out, x minus, and then you drop those numbers in. So I would put in root 3i and negative root 3i.
So in this scenario, would plus or minus 2i also be a solution? Square root doesn't be the square root.
Where do you see 1 plus or minus 2i?
Because the square root of 3. But then if so, oh,
Okay. Okay, but now this can be cleaned up a little bit. We would now call it, the final answer is 4 x minus 1/2 squared times x minus root 3i and x plus root 3i. And that is done. So make sure you get all the way down to there. That's your final answer. And now, at the end of all that, you might say, and I hope you do ask this question, am I right? Is that correct? And of course, what's one way you have to check? Well, yeah, it's true. You could plug all of those answers. You could plug in a half. You could plug in positive root 3i. You could plug in negative root 3i back into the original quartic and actually work it all out. And that would be so painful. I wouldn't even want to do it. And I'm super geeky. I love checking my answers, but I wouldn't even want to do that. So instead, what we could do is just graph the original and our answer side by side and see if the graphs overlap. Right? Because if I now type in the answer and the graphs overlap, it must be that my factorization is correct because it produces the same graph. So the thing is, Desmos does not understand I don't think. So if I type in x minus square root 3 I, it thinks I is a coefficient of some sort. So it's not going to do the right thing here and actually be able to graph that. It doesn't know what that is. So instead I go back a step before I got the I, and I would graph x minus a half times x minus a half and 4x squared minus 12. Wait, not minus 12. What was it?
Plus 12.
Yeah, plus 12. Wow, isn't that a huge difference the plus and the minus make? My goodness, look at that. That's with a minus, and then that's with a plus. So what do you think? Does my graph perfectly overlap the original? Yeah. And so that gives us great confidence that our answer is correct. Right? We always want to be able to ask the question, am I right? Both in our personal lives and in mathematics. We want to know, okay, was that correct? Is this the right decision? And so yes, it is. Alrighty. I tell you what, number 16, I don't think we'll do number 16 because I want to keep plenty of time for our other, our next chapter. But just so we all see it, and you can all write it down. Whoops. Oh no, I have my caps lock on. Oh, x to the 5th, that's x to the 4th, 7x cubed, minus 7x squared, plus 12x minus 12. All right. So look at this polynomial. What does that tell us? This thing is an x to the 5th, right? So this last one, number 16, is x to the 5th. How many solutions will there be? There will be 5 solutions. How many x-intercepts are there? Only 1. So let's just talk about what that means for the answer. This would be interesting to write down. So let's all write down, what does that mean about our answer? So when my original quintic, which was f of x equals x to the 5th, etc., what we're going to end up with is 1, 2, 3, 4, 5 factors. And only the very first one will have a real number in it. And what is that x-intercept? 3? No, 1. All right, so I know that my first factor is 1. So what about the rest of these? What numbers will be in each and every one of them? I. Every single one of them will have an I. But here's the cool part. Going back to what we said, what neat thing happens when you multiply conjugates together? The product becomes a real number. Because all the coefficients of this polynomial are all real numbers, my imaginary roots come in conjugate pairs. So just making this up, let's say that the first one was x minus 4i, then the other one is going to be x plus 4i. You'll be able to immediately see that you've got a pair there. And then whatever the next one is, let's say it's x minus 2 minus 3i, then I already know the next one is x minus 2 plus 3i. And so that's kind of nice to know that when you do factor larger polynomials, the imaginary answers come in conjugate pairs, and that's a guaranteed result. So as soon as you find one, you automatically have the other. All right. Well, I think there's just one problem left, right? Number 17. Is that the end of the packet? All right. Well, let's do it. You know, folks, you're all amazing poker players because you all have such a straight face on. But I know that you're having the most ecstatic time of your life right now. I know that you're sitting there like filled with joy, like, oh my gosh, this is amazing. We're factoring polynomials and imaginary roots. This is the best time I've had in a week. And then you have such good poker faces right now, like. Okay. So what's the last one? Here's our last problem. Number 17. It says create a polynomial with real number coefficients which has all of the desired characteristics. You may leave the polynomial in factored form. Well, thank goodness. So, last one, number 17. I brought tons of good markers today, and yet somehow I keep using the bad ones. Where did all my good markers go? Ah, that's why, in the box. All right. So, what do we want to know? The zeros of f are plus or minus 1, plus or minus I. So, how many roots do we have? 4. So, let's go ahead and write down f of x equals factor, 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 factor. We know that my roots are, I'm going to write solutions. Like the solutions are 1, -1, 5, -5. And we know the leading term should be 42x to the fourth. We'll go back to that. So start by writing out x minus, x minus, x minus, x minus. And again, whatever your solutions are, you just drop them in. You drop them in to those empty waiting parentheses. So I'm going to have a 1, -1, I, -I. And so just to clean that up a little bit, it would actually be f of x equals x minus 1, x plus 1, x minus I, x plus I. And the fact that we want the leading term to be 42x to the fourth, what do I have to put up front? 42. That'd be it. That's the end of that problem. Now, somebody asked me a question about a problem that was on the homework, and oddly enough, we haven't seen it yet in our notes, which blows my mind because I remember doing these problems in the notes last year, the last semester, and yet somehow, apparently, I'm not in the notes. Oh my goodness. Oh no, it's not letting me log in. Wasn't letting me log in because I was using the wrong password. I'll explain it. All right, does anyone recall what the problem was? Chapter 3, probably, it wouldn't be 3/4, because we hadn't gotten there yet, probably here. The 10th version. Aha, number 7. Let's look at number 7. All right, folks, this is a really good problem. If you don't have somewhere to write this down, take out a sheet of lined paper, write it down, make a little note that this is one of your homework problems. It's a really good one. It'll be on the practice test, so we'll definitely look at this again. So this is more 3-2, number 7. So what does it say? We have a polynomial of degree 4, so we can already set that up. I know that my p of x will be something, 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 something. It has roots of multiplicity 2 at x equals 2. So that means that x equals 2 is a root twice. So that'd be x minus 2, x minus 2. And it also says we have a root of multiplicity 1 at x equals 0 and x equals -2. So I know that x minus 0 is one of them, and then x, the root is -2, so that means x plus 2. So how's that so far? So far, we've just put in all of our x-intercepts. Now, one thing we've seen in previous problems like this is that there's often a coefficient out front, and just a number. There's often a number out front. And the thing that they haven't told us yet is what that number is. And so what we're going to do is write down the letter C. C just stands for coefficient, stands for some number. We don't know what it is. It could be 1, it could be 42, it could be positive, it could be negative. It's just some coefficient that we don't know yet. So the last piece of information they tell us is that this polynomial should go through the coordinate 563. So let's think about what that means. If it goes through the coordinate 563, what does that mean in terms of input-output? If I plug in 5, what should the whole thing equal? Should equal 63. So let's try it. If I plug in 5, so P of 5 equals C times 5 minus 2, 5 minus 2, 5 minus 0, 5 plus 2, should equal 63. That's a really interesting example of input-output, allowing us to now work backwards to solve what that coefficient is. So now, just focus your attention on the actual equation and the fact that we want to solve for C. That is, in fact, the purpose of this question. Solve for C. solve for the coefficient. In previous problems, they just told us the coefficient. In this particular problem, they're asking us to solve for that coefficient, and they're doing it in a clever way. Notice in the previous problem, they said, I want the leading term to be 42x to the fourth, so we knew that the coefficient would be 42. But in this problem, they're saying, I want this polynomial to go through that coordinate. And so by plugging in 5, setting the whole thing equal to 63, we can now solve for c. So what do we have? C times 5 minus 2 is 3, 5 minus 2 is 3, 5 minus 0 is 5, 5 plus 2 is 7. I now know that c times all those numbers should equal 63. Well, I'm going to go ahead and multiply all those numbers. So 3 times 3 times 5 times 7 is 315. So now I have 315 times c is equal to 63. And I want to solve for c. So c is being multiplied by 315. So we divide by 315. And that tells me that c is equal to 63 315ths. That is really arbitrary and ugly and not a pleasing result at all. It'd be nice if the coefficient had been like 4. But it's that. Now, everybody, if you type 63 315ths in your calculator and then hit math frac, it'll tell you the fraction, or it'll reduce it for you. It's 1/5. 1/5, or you could say 0.2. Because when I typed that in initially, it just gave me 0.2. So 0.2, that's pretty nice. So now what does that mean? Now that we have solved for c, that tells us our final answer. Just like previously, we just stuck a 42 out front. In this problem now, you would stick a 0.2 or a 1/5 out front. And you would say the polynomial that has the desired characteristics is 0.2 x minus 2, x minus 2, x minus 0, x plus 2. Notice I just put x, because x minus 0 is the same as x. And now I put a 0.2 right there, because just so you know, if you choose to put 1/5 right there, make sure you put 1/5 in parentheses. If you don't put 1/5 in parentheses, more, or your calculator, or Excel spreadsheets, well, it might accidentally confuse 1 divided by 5 in front of all that, and they might think you mean 1 divided by 5 times x minus 2, etc. And my goodness, that would have just stuck all over your factors in the denominator, which would be a totally different function, not the function you meant. So make sure if you put a 1/5 out there, you put it in parentheses. I'm not sure if the person who asked me about that is in this class or in the other class. I forget now off the top of my head. But did this answer your question?
Yes.
Okay, super. Anyone else? Any questions about the homework right now while we're here? Hey, just in general, please email me. You know, as you're sitting at home doing your homework, email me. I know that. See, I know that there's this hesitancy for students to email the teachers, like, no, I don't want to bother the teacher. No, I don't want to email the teacher. But here's the thing: you're paying me. You're paying me to email me at midnight and respond to you. No, I'm kidding. I'm not going to respond to you at midnight. All right? Got kids. That's not going to happen. But if I happen to wake up at midnight and I check my phone and I see an email, I'll reply. So please, I want to encourage all of you, you need to take advantage of your teachers. Take advantage of the fact that, you know, when you pay your tuition, sure, I show up in class and I'm here and I talk to you about math. But you know what your tuition buys you? You know what your tuition buys you? A human being who is required to respond to your emails. All right? That's what your tuition buys you. I am required to respond to your emails. Not only that, I like responding to your emails. But I just please hope you know that your teachers, they are your paid employees. Is that weird? To call your teacher your paid employee? They are. They're your paid employee. They're required to do what you ask them. So I say that because not a lot of you are emailing me, just some of you. But I would really like all of you to be emailing me with your questions. Okay, I'll get off my soapbox. So now what? We're done with chapter 3. So, changing gears. I'm going to do a little introduction to chapter 4, then we're going to take a break. So, chapter 3 was all about polynomials. And what was our end-all be-all goal of this polynomial here? Well, there were multiple goals. What was one end-all be-all goal? That you should be able to look at a polynomial like that and do what to it? Graph it. That's the big picture, is to be able to graph it, find the x-intercepts, y-intercepts, and the end behavior. But kind of, what was our intermediary goal? Our main goal was to change this addition problem and turn it into a multiplication problem. Our goal was to factor it. And so, as we switch now to chapter 4, we're basically just going to still continue studying polynomials The only difference is we're now going to put a polynomial over a polynomial. We're going to make fractions out of polynomials. And that's what rational even means, ratio null. It just means a function that's now a polynomial over a polynomial as a fraction. And what's really interesting here is that each polynomial is going to give you different information. Okay? So whereas previously, when I factored this polynomial, what did each factor tell me? An x-intercept, right? Now down here, when you factor the numerator, those factors in the numerators will continue to give you x-intercepts. But in the denominator, these factors are going to tell you something completely different. Okay, so now that we're in chapter 4 and we're looking at a polynomial divided by a polynomial, the numerator polynomial, if you factor it, is still going to tell you x-intercepts. The denominator polynomial, when you factor it, is going to tell you something else. And the thing that's something else is kind of interesting. So we're going to look at rational functions. And we're going to start by looking at this paper here. So if you would have that one out on top, properties of rational functions, mat150. Did everyone get one of those? All right, it was in the back. But before I even show you that sheet, I want to put you in the right mindset. And I want you to be in the mindset of a zoologist, right? Like a zoologist. Like let's say that you're about to go to a new zoo for the first time ever. And you just go around, and what do you do at a zoo? You just walk around. What, Jessica? You just walk around and look at the animals. You're like, oh, look at that animal. Huh? Oh, look at that animal. Huh? Oh, look at that one. Huh? Like, how interesting. That's what all these animals look like. Or better yet, you go out in nature and you're just walking around a forest. And you're like, oh, look at that. Like, there's that animal. Oh, look at that. There's that animal. Or better yet, you get to go to another planet where there are creatures existing. And you're like, whoa, now really check it out. Like, look at these animals. Like, this is interesting. And that's the attitude I want you to bring to Desmos right now. So take a look up here at Desmos. And I'm just going to type some things in. And you're going to look at what the picture is. And you're going to say, oh, interesting. Look at that function. All right? So first of all, let's start by typing in the normal, which would be a polynomial that's already in factored form. So I'm going to do x minus 1 and x minus 4 and x minus 7. Okay? So there we go. Got myself a nice little polynomial, right? We know everything about this polynomial because we've just been studying it. No surprises here. The one thing I'm going to do is put a coefficient on it of maybe 0.1 to just shrink it down a little bit. There we go. So everyone feel very confident and comfortable with what we're looking at? It's a polynomial. Are the x-intercepts where you expected them to be? Yeah. And is the y-intercept? Well, we would have to, multiply out 1 times 4 times 7, which is 28. I put a coefficient of 0.1, so that's 2.8. And sure enough, the y-intercept is a negative 2.8. Okay. So now, I'm going to put something in the denominator. I'm going to put a factor in the denominator. And where am I going to put it? I think I'll put it at 2. Okay, so I'm going to put an object in the denominator at x minus 2. Oh, whoa. What just happened? That's weird. Something really strange just happened. Now, first of all, where are my x-intercepts still? Are they still at 1, 4, and 7? Okay, well, that's good. Right? That means that my x-intercepts in the numerator have remained my x-intercepts in the numerator. But something wild has happened because I put in an x minus 2. Now watch, I'm going to give it an exponent of 0 to make it go away. So anything to the power of 0 is just 1. So now that factor's gone again, and there's my normal thing. So again, x-intercepts at 1, 4, 7. But now let's really think, what's happening at 2? Because x minus 2 would represent an x-intercept of 2. And yet by putting that thing there, did I acquire an x-intercept at 2? No. In fact, there is no x-intercept at 2. In fact, there's nothing at all at 2. In fact, what is at 2? What now exists at 2? Do you know what the name for that is? Asymptote. This is an asymptote. We now have an asymptote. I'm going to put in the vertical line x equals 2 so you can more clearly see it. A vertical asymptote means that the graph goes up, 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 and never quite reaches it. And it comes down, 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 and never quite reaches it. So I just inserted, by putting that factor x minus 2 in the denominator, I did not create an x-intercept at 2. I created a vertical asymptote at x equals 2. I'd like to create a new vertical asymptote, and I'm going to create it at 5. I'm going to create a vertical asymptote right here at 5. So I'm going to put another factor down there, x minus 5, and whammo, I now have another vertical asymptote at x equals 5. Observe, x equals 5. There it is. My graph approaches it from the left, but never touches. And my graph approaches it from the right, but never touches. What do these graphs now do? How high up does that line go? Infinitely far. So notice, do I still have x-intercepts at 1, 4, and 7? Yeah, the x-intercepts have remained untouched. The numerator has remained untouched. But I now, by putting those factors in the denominator, I just created vertical asymptotes at those spots. So let's see, I'm going to be crazy here, and I'm going to put one at -2. So I want an x-intercept at I want a vertical asymptote at -2. So I'm going to put in x plus 2 and a whammo. I just created a new vertical asymptote at x equals -2. Now what does my graph look like so far? It's weird, right? This is definitely like a creature at a zoo on another planet. Like, what's going on here? Yeah, you got a thing here, goes up to infinity. You got another fella here that goes down to infinity and up to infinity. Another fella here, down to infinity, up to infinity. And then another fella here that comes up from -infinity and then just kind of goes over to the right. This is a pretty interesting creature. And if I wanted to, I can just keep on creating vertical asymptotes. I'll put another one at -5. Bammo. Now I have another vertical asymptote. And I can put a vertical asymptote all the way over there at 10, x minus 10. Now I have another vertical asymptote. Now you notice that my graph is becoming a little harder to kind of see what's happening. I need to adjust my scale. -0.5, 0.5. There, kind of prettier. So I think I probably already said it, and you probably all appreciate now what we're looking at. My numerator factors are all of my x-intercepts, and they remain untouched by all the craziness that I'm doing by inserting factors in the denominator, which creates vertical asymptotes. And that's kind of it. There's chapter 4 for you in a nutshell. All right, chapter 4, we're going to be studying the combination of x-intercepts in the numerator and vertical asymptotes in the denominator. And then curve sketching, right? Curve sketching. If somebody just walked up to you and they were like, hey, here's a, oops, there we go. Here's a rational function right here. I want you to sketch a curve of that. And then that would be your job. You know, here's an unknown function. I want you to graph what that looks like. Yep. Everyone really excited? So what are we studying? Rational functions, polynomial divided by a polynomial. What information does the numerator have? All the x-intercepts. What information does the denominator have? All the asymptotes. Probably a really nice thing to do right up front before we do anything at all is to draw a picture of that. Like a little handy formula. Like this is our formula now. So if I wrote f of x equals a rational function, I now know that I've got a whole bunch of factors in the top, a whole bunch of factors in the bottom. And the factors in the top, those are x-intercepts. And the factors in the bottom, those are vertical asymptotes. Now, we still have a lot left that we need, right? What else do we need? Because previously with polynomials, we want x-intercept, y-intercept, and behavior. So what else do we need? We still need the y-intercept, which fortunately is really easy because y-intercept is always the same. No matter what, if you want the y-intercept, what do? You just plug 0 into the function, right? So we can very easily get the y-intercept. You just plug 0 in. So I'm going to put a little 0 here, plug in 0. And that's the y-intercept. Okay, so that's our x-intercepts, our vertical asymptotes, plug in 0, that gives you the y-intercept. What else do we need? End behavior, okay? And then the end behavior, there's a couple more things that we need to capture end behavior. One is just overall, you know, how do you sketch the graph by hand? But the other is, there's one other feature of a rational function that we didn't really look at. Not only is there a vertical asymptote, wait a minute. What's going on here? That's a weird one. What? Oh. Oh. There we go. Not only are there vertical asymptotes, what other kind of asymptote is there? There's a horizontal asymptote as well. So we'll also be interested in the horizontal asymptote, the fact that, you know, as this green line now goes to the right, it's asymptotically approaching the x-axis. So not only do we need to know how to sketch this whole thing, but we need to understand horizontal asymptotes. So that's interesting. A rational function not only has vertical asymptotes, it also has horizontal asymptotes. And this is the new creature that we're about to study, okay? So this is a whole new type of creature because it's a fraction. We've got numerator information, denominator information, vertical asymptotes, horizontal asymptotes, and that's what we're about to study. So I hope that gives you a nice kind of big picture view of the types of animals or graphs that we're about to look at. So let's take a break. Time is now 9:11. So let's all come back at 9:20.
Ava got your email.
Awesome. I have a quick question.
Mm-hmm.
If I was to go about doing 15 with the quadratic formula,
Yeah.
It basically brought me to this, which got me to this,
Right.
which got me to this.
Yeah.
I'm trying to figure out how you get the 4 in the front though for this.
Well, because before, right here, you would need to take the 4 out now before you do the quadratic formula.
You would.
Because, yeah, see, the quadratic formula is going to give you the x-intercepts. But that doesn't account for the fact that there could be a coefficient out front. Like, for instance, watch this. Watch. This is very interesting. So in Desmos, I'm going to build a formula. I'm going to build a function that has x-intercepts at obviously x minus 2 and x minus 5. Okay? So there we go. I have my x-intercepts. But now I can put any number I want out there, like a 2. Still has the same x-intercepts. I'm going to put a 3. I'm going to put a 4. I'm going to put a 5. So there could be a coefficient out there. You just don't know. And it has the exact same x-intercepts every time. So what the quadratic formula gives you is just the x-intercepts without any knowledge whatsoever about what that coefficient out front could have been. And so you have to maintain that information from the 4 right there by factoring the 4 out so that the 4 goes out front of the function. And then what you're left with is x squared plus 3. And if you did 1x squared plus 3, if you did the quadratic formula on that, you'd get the exact same result, square root of negative 3.
Okay.
So yeah, the 4 has to come out first. In fact, there's like this general idea. The general rule is if you're looking at a polynomial and you can factor things out, do that first.
Do it.
You got to do it immediately before you then proceed to do anything else.
Got it.
Yeah, that's a really good idea. I should stress that.
All right, thanks.
Sure. Oh, that's good. All right, folks. Everyone ready? Everyone excited? Everyone stoked? Ready to keep going?
Let's do it. So what I have for you here is an introduction. It's an introduction. We're just going to move right along through it, take a look at what it says. It's an overview. I'm not going to collect it for anything. In fact, what it is it's a gift. You can take it home. You can put it under your pillow. You can hang it up on your fridge. You can frame it. You can give it to your kids. It's just a nice overview of rational functions and how they work. So let's go ahead and move it along through the example here. So first, it says, consider this rational function. Okay, it's a polynomial divided by a polynomial. A parabola divided by a parabola. The graph is shown at the right. So there's the graph at the right. Now, I want you to notice, and go ahead, trace it in the vertical asymptote at x equals 5. So you're going to put a little dotted line there. Go dash, 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 dash. Put in your dotted line there, and that's the vertical asymptote at x equals 5. Also notice that that is not a typo. That is a hole. There's a hole in the graph. Now, there is no actual circle there. There's just a hole, denoting the fact that if you were moving along, moving along, moving along, then right there at x equals negative 3, there would actually be a gap in the graph. There would be nothing there. There would just be a void, okay? No point there at all. But otherwise, the graph is what it appears, okay? So you have a vertical asymptote at 5. This is a horizontal asymptote. It's getting lower and lower and lower. This one is a horizontal asymptote. It's getting a little higher, higher, higher. And you have a hole right there. So this is what we see. So why does the graph have the properties shown? The major goal in this course is to be able to match our understanding of a function with its graph. So if you just look at the function, you should be able to make the graph yourself. And if you just look at the graph, you should be able to figure out what the function is. That's how these two skills go hand in hand. You should be able to find a perfect relationship between the function and the graph and be able to create the other from the other. That makes sense. Okay. So, why does the graph have the properties shown? The answer is, first, and the most important observation about a rational function is this. Because there are variables in the denominator, are there variables in the denominator? Yes. The denominator could equal 0 if you plug in the right input. So, for instance, if I find just the right clever input to plug in down there, that whole denominator could become 0, which is undefined. And an undefined denominator creates one of two objects. It either creates a A vertical asymptote or a hole. Okay, so anytime you divide by 0, you either just made a vertical asymptote or you just made a hole. You don't know which yet, but it's one or the other. So dividing by 0, that's kind of fun and interesting. On a calculator, if you divide by 0, it says error. You say, well, dividing by 0 is an error. But in fact, graphically, dividing by 0 is something. Dividing by 0 on a graph is a vertical asymptote or a hole. So dividing by 0 does produce something. It produces something visual, an asymptote or a hole. Okay, so however, as a basic rule of math, we are never allowed to divide by 0. And so we perform 3 steps with the denominator of a rational function. So this is the very first thing you do. The first thing you do is factor the denominator. Okay, you have to factor both. Okay, that's just part of the job. You're going to have to factor both of those. As a basic skill, we now assume that you can factor any polynomial I give you. So if I give you a polynomial, boom, first thing you do, factor it. Right? Synthetic division, factoring, quadratic formula, whatever you have to do, first thing you do, factor those polynomials. Okay, so what are you going to do? Number 1, find the domain of the function. That is, remember the values of x that you cannot input into the function. So we've done that many times now. When you have a function, and I'm just going to make it simple, let's say that f of x is equal to 1 over x minus 2, x minus 4. What's the domain? The domain is all real numbers except 2 and 4. Remember, the domain is every number in the world that you can plug in, except those numbers that would cause you to divide by 0. And so if I let x be 2 or x be 4, you automatically know that x can't be 2 or 4, because then 2 minus 2 would be 0, and it would be 1 divided by 0, or 4 minus 4 would be 0, and 1 divided by 0 would be undefined. So already I know that 2 and 4 are not in my domain. I'm not going to ask you to do the whole, I mean, you can. You could say, okay, well, therefore my domain is open circle, shade everywhere else. And therefore my domain would be negative infinity 2, union 2 to 4, union 4 to infinity. Okay, of course we can still do that. But the important thing is to notice it can't be 2 or 4. And in this particular case, what I want you to know is that 2 and 4, they're either asymptotes or holes. Okay, so any number that you exclude from your domain, it's either an asymptote or a hole. You just don't know yet which, they could be both asymptotes. They could be both holes. That one could be a hole, and that one could be an asymptote, that one could be an asymptote, and that one could be a hole. You don't know yet. But let's all agree, just right up front, that if we're going to abbreviate and you write asymptote or hole, don't actually read that out loud because that'd be terrible, right? I'm making a joke. Asymptote hole. Okay, never mind. Good, I ever said it. Let's keep going. Okay, so first thing you do is find the domain, because whatever numbers you exclude from the domain are holes or asymptotes. So first you find any holes in the graph, and then you find any asymptotes in the graph. Now the good news is the holes are the binomials that can be canceled, and the asymptotes are the binomials that are not canceled. So let's take a look at that example. Let's actually see what that means. So 1, find the domain. So fill this in. The domain is defined to be all numbers you can plug in except for those that cause you to divide by 0. Right? You don't necessarily have to write the whole thing if you remember. So the domain is all real numbers except those numbers that would cause you to divide by 0. Thus, our job is to find out when the denominator is equal to 0. So does everyone agree that this is our denominator for my rational function? So you take x squared minus 2x minus 15, you factor it by just saying what multiplies to make 15 that adds to make 2. So I got x minus 5x plus 3. I go ahead and finish the 0 product rule, and I find out that 5 and negative 3 are not allowed in my domain. And I just say, since plugging 5 or negative 3 into the function will make the denominator equal 0, we'll exclude the values 5 and negative 3 from our domain. And right now, I just hope you notice that, in fact, 5 is the vertical asymptote, and negative 3 is the hole. Right? Do you see that on your graph? Okay. So, thus, the domain of this function is all real numbers except 5 and negative 3. And you could write that domain out in set notation. You could say the domain is all real numbers x such that x isn't 5 or negative 3. Or you could write it out in interval notation, like I just did in my example. The key thing is, now that we have the domain, we want to go a step further and say, okay, what is it? Is it an asymptote or is it a hole? So, number 2, find out if there are any holes. In order to find out the holes in the asymptotes, you first have to completely factor the original function. So notice, this is what we started with, but after factoring, we get this. Okay? Again, we just take it for granted now that you're able to factor anything you see, and you just do it. Right? So bam, bam, you just factor those into this. Now notice what you have. What are you really tempted to do right now? Cancel out those x plus 3's, because you get it simplified. So once a rational function is factored, we are allowed to cancel, that's your word there, cancel, any binomial terms that are in both the numerator and the denominator. And by definition, the whole is represented by the binomial that you cancel from the rational function. Thus, the term x plus 3 represents the whole. Okay? So when you factor a rational function and you get to cancel something, those are wholes. Every time you go ahead and do it right now, go / and label whole. Okay? Do it with your hand right now. So / write whole. Anything that you cancel is a whole. And as always, since x plus 3 is the factor, where's the whole actually? At -3. Right? So -3 is the location of the whole. So any term you cancel, that's a whole. 3, find the asymptotes. The asymptotes are whatever's left. So by definition, the asymptote is given by any binomials that you cannot cancel from the denominator. So after canceling the x plus 3 term from the top and bottom, now we just have this reduced polynomial, this reduced rational function. We are stuck with the x minus 5 term in the denominator. There's no canceling that one. And therefore, that x minus 5 term represents the asymptote, and since it's x minus 5, the asymptote is actually at +5. So x equals 5 is the location of the asymptote. Okay, that's it. Pretty basic. You take a rational function, you factor the top and bottom, cancel anything if you can, those are the wholes. Whatever you can't cancel in the denominator is the vertical asymptote. So conclusion, here's a nice little step-by-step process right there. And I want you to write this in, okay? So you have your polynomial, you factor it, go ahead and below that term that you crossed out, write whole. And below the one you don't cross out, write asymptote. That should be just something you just do. As soon as you cancel out a term, write whole underneath it. If you don't cancel out the term, write asymptote underneath it. Or again, if you just want to abbreviate, you can write asy or asym or asym. I don't know. You could even just write H and A. That's totally fine. You just want to write H and A, and we all know that that represents a whole and an asymptote. That'd be nice and quick and simple. So here are our conclusions. The domain is all real numbers except those inputs that make the denominator equal 0. Therefore, the domain is everything in the world except 5 or -3. Specifically, the wholes are given by the binomials that are canceled, so the whole was at -3. And the asymptotes are given by the binomials that are not canceled, and therefore our asymptote was at 5. And that's it so far. It's just a nice, quick introduction to rational functions. How do you feel about that so far? Now, I didn't prove any of this to you. I'm just giving it to you. Like these are the definitions. This is how it works. Okay, now, how do we build our graph? Thus far, we have only considered the denominator of a rational function. The denominator is the vertical asymptotes. The numerator is the x-intercepts. There's more to say. So the denominator of a rational function is especially important because it might equal 0, as we put right there. The denominator is the first thing we focus on, because if it equals 0, then that's a domain exclusion, and it's either a whole or an asymptote. So the denominator gets the majority of our focus. We go straight to the denominator and say, hey, what's going on in that denominator? But what about the numerator? You know, what's going on up there? We know already that's the x-intercepts. But what about the fraction as a whole? What if you consider the whole fraction? What other information can you get out of it? So in general, we would want to ask all of these questions. We'd want to say, what's the y-intercept? What's the x-intercept? Where are the vertical asymptotes? Where are the horizontal asymptotes? Now, this is a complete analysis of a rational function. We need to be able to answer all 4 of those questions. So let's consider each one of those. And again, we're going to look at the exact same graph. So here's our same rational function. That's our same graph with the whole and the asymptote. And let's try to answer all of those questions. Probably be helpful if I had this on the screen so that we could actually see it. You think I can just, I'm gonna have to turn the other way. I'd like to write on this with you. So I'm gonna don't mind me, Chelsea. I don't think I'll fall on you. If I do, please don't let me hurt myself. There we go. All right. Because it might be equal to 0. Yeah. Oh, not far enough. right. Well, it's a little slanted, folks. I hope that you'll forgive this weird experience for the next 20 minutes. You can always just turn your head. You just go like that a little bit, everybody. Just turn your head. All right, where's my eraser? There it is. Here we go. So here we go. What is the y-intercept? Well, what does every y-intercept have in common? Just draw a quick little picture. If you have a y-intercept, you know that it's of the form 0, 5, or something like that. Right? So what does every x-intercept have in common? The 0. X is 0. Therefore, every y-intercept has the form 0, something. I just put a pound sign for a number. Thus, for every y-intercept, the x-coordinate is equal to 0. And this tells us that if you want to find a y-intercept, let x equal 0. And that's what we've been doing all along. That a y-intercept, if you look at a graph, the y-intercept is always f of 0. So if you want the y-intercept, just plug in 0. Now notice, that's really easy to do. Because the numerator and denominator are both polynomials, and any term that has an x in it, you plug in 0, is just 0. So what's the only thing you have to look at? Those last two numbers at the end, because all of those become 0. So f of 0 is -3 over -15, which reduces to 1/5, which is 0.2. So where is our y-intercept? You can see it on your graph. Everybody put a little dot and label it 0.2. So how do you find the y-intercept? Plug in 0. Right? Just plug in 0, and there's your y-intercept. Okay, so what about the x-intercept? Well, we already know all about x-intercepts. What does every x-intercept have in common? Again, just remind ourselves, if you got an x-intercept here, that x-intercept would be something like 8, 0, and this x-intercept would be something like 4, 0, and therefore every x-intercept has in common the fact that y is 0. Thus, every x-intercept has the form number, 0. Thus, for every x-intercept, the y-coordinate is equal to 0. I realize I'm repeating myself here, but I'm hoping that you're nailing down this chain of logic in your mind. That if somebody just came up to you and said, find the x-intercept, you'd be like, okay, well, how do I find an x-intercept? I mean, I guess I know that means y has to be 0, so that means y has to be 0. So this tells us that if you want to find the x-intercept, let y equal 0. So we set the entire function, right, because this whole function is f of x, and f of x is y. And so if we want to let y equal 0, what do? We set the whole thing equal to 0. Right, so this is a chain of reasoning that I've provided to you here. It's a chain of reasoning that you'd be able to figure this out on your own. How do you find an x-intercept? You set the function equal to 0. And remember, we already knew that. That's one of the first things that we talked about in class. But if you want to find an x-intercept, you set the function equal to 0. Okay, so now, big question. How do we solve that thing? How do we solve for x? We've got x is in the numerator, x is in the denominator. Looks pretty complicated. Looks a whole lot harder than, 3x plus 5 equals 12. That'd be very easy. So how do we solve this thing? Yeah, we try factoring it, and at some point we will factor. Seems pretty complicated because we couldn't use the quadratic formula because there's two parabolas there, and one's in the denominator. Right now it looks pretty challenging, but there's a quick trick we can do that's going to make it a lot easier. Anybody? Any thoughts on what we could do? We cannot cancel out the x squared. Thank you for suggesting that. We cannot do that. Why are we not allowed to cancel out the x squared? Because they're addition problems. Exactly right. You can never cancel something if there's an addition problem. You can only cancel if it's a multiplication problem. So the fact that there's a plus sign right there definitely can't cancel out the x squareds. Any other thoughts on what we could do to solve this thing? Times the bottom number times the top. Part of what you're saying is definitely what we're going to do, but the way you said it right then would not be accurate. Like if I had the fraction 2/3, and then I just multiplied 2 times 3 to get 6, nothing about 2/3 is equal to 6. So what did you mean by that? Yeah, absolutely, folks. Like consider a basic algebra problem like x over 5 equals 20. X is being divided by 5, so what do? You multiply both sides by 5. And why did we multiply both sides by 5? You're going to cancel it, right? And so what better thing to do with this denominator than cancel it? That'd be great. We can just cancel it. So everybody, go ahead and multiply both sides by x squared minus 2x minus 15. Put it in there, x squared minus 2x minus 15. And notice how glorious this is. What happens on the left? The whole darn thing cancels out. What happens on the right? 0 times anything is 0. Wow. I mean, we just completely dispatched the denominator completely. And now all we have left is x squared plus 2x minus 3. We just really drastically simplified this algebra problem by just getting rid of the denominator. Okay, now going back, I think somebody mentioned, what do we have to do now, of course? We just factor it. So what multiplies to make 3 that adds to make 2? I think it's x plus 3x minus 1.
Yes.
And therefore, our solutions are x equals negative 3 and x equals 1. So notice then, if we want to find x-intercepts, what do we ultimately do? Well, that's true. We do that. We get rid of the denominator, which means the denominator is not even part of our analysis. If we want the x-intercepts, we only look at the numerator. And so you can just take the numerator. You can just take the numerator, factor it, those are your x-intercepts. So that's the answer. If you want your x-intercepts, just look at the numerator, factor it, those are your x-intercepts. You can basically ignore and disregard the denominator. Okay, so however, remember that x equals negative 3 was a whole, so it can't be an x-intercept. That's a little subtle, right? I just told you that we just found the x-intercept, right? But is negative 3 an x-intercept? No, it's a whole. So there's some subtlety there that you would want to reduce your polynomial first. You would want to get, you'd want to get this to whatever the reduced form was. What did it reduce to? Is it on your page? It actually reduced in the previous step or on the previous page. We got it to reduce to x minus 1 over x minus 5. We got it to look like this. So what's our only actual x-intercept? The 1, right? Because that was actually a whole. So right here, we might want to go ahead and rewrite whole. So one part of the analysis says negative 3 is an x-intercept. The other part of the analysis says that negative 3 is a whole. The analysis that negative 3 is a whole wins because there was an x minus 3 in the denominator too, which means dividing by 0. So that was a whole. That's our only actual x-intercept. Okay, let's keep going. We now know how to find y-intercepts and x-intercepts. Where are the vertical asymptotes? Where are the vertical asymptotes? No, those are just the denominator. So we've seen that. If you want vertical asymptotes, you just look at the denominator. There we go. So we already know the answer to this. You'll have a vertical asymptote wherever the factor in the denominator does not cancel. Right, so in this particular case, we had x plus 3, x minus 1, and x minus 5, and x plus 3, and the 3's canceled out, which gave us x minus 1 over x minus 5. So this was our only vertical asymptote. It was the only factor in the denominator that didn't cancel out. Now I have a bonus question here for you. I don't think I'll answer it today. I want you to think about it. Why does a factor in the denominator create an asymptote anyway? Why does it create an asymptote? That's a really good question. Why does it create an asymptote? Like here we had, I built this simple function where I had, just a normal parabola here. And then I wanted to put in an x-intercept. So hold on a second here. And so I'm going to create a asymptote, say maybe at 2. And so down below I put in x minus 2. Why does that suddenly cause our function to go shooting up to infinity and shooting down to infinity? like before I put that factor in there, it was just a nice little parabola. And the parabola only went so far down as that point. But all of a sudden, by putting a factor in the denominator, it caused my function to shoot down to infinity and to shoot up to infinity at that point. Why does that happen? I just want you to play with that. Go home, think about it, have a fever dream or two, and think, why does something in the denominator cause an asymptote? Specifically, why does it cause the value of the function to increase to infinity and to decrease to negative infinity? So I'm just planting that question in your mind, and you can think about it. Okay, last question. What are the horizontal asymptotes? So, how do we find horizontal asymptotes? A horizontal asymptote occurs when you go very far to the right and very far to the left. Okay, so can we just agree that that's a basic definition of a horizontal asymptote? The horizontal asymptote means what is the end behavior when you go to the right, and what is the end behavior when you go to the left? So what does that mean to go very far to the right? What is my x value when I go really far to the right? X is positive infinity. And what is my x value when I go very far to the left? X is negative infinity. So we could find the end behavior by plugging positive infinity in for x and plugging negative infinity in for x. Well, now infinity is not really a number. You can't plug it into a function. But you kind of can. So let's talk about it. A horizontal asymptote occurs when you go very far to the right or very far to the left. And in words, as you go as far to the right and left on the graph, what does your function approach? So as you go far to the right and left on the graph, does your function approach a particular value? Okay? Like for instance, contrast that with a parabola. As I go very, very far to the right, is my function, is my y-coordinate approaching a particular value? No, it's just going up to infinity. Whereas with a horizontal asymptote would do this. It would level off at some value like 5. So in this case, an asymptote, as I move to the right, my function approaches a particular value, 5. That's what a horizontal asymptote is. In a parabola, as I go to the right, it just keeps going up, 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 up forever. But with a horizontal asymptote, it goes up, and there's a limiting number, 5. So as you go to the far right and the far left, does your function approach a particular value that is getting closer and closer and closer to it? That's a horizontal asymptote. So to determine this, we follow this process. So how could we do it? What I'd like to suggest here is, well, I'll just say it. You look at the leading terms. Make the ratio of the leading terms and so by leading terms, we're only looking at the first two terms. The first term of the numerator, first term of the denominator. And in this particular case, the ratio is 1x squared over 1x squared, which simplifies to 1. The x squareds cancel out. 1 over 1 is just 1. So that's just 1. That is the horizontal asymptote. And everybody, if you go ahead and look at your graph, is that true? Look at the y-axis, mark it with a 1 right there. Is your graph getting closer and closer to the horizontal line 1? Yeah, and is it coming up and approaching the horizontal line, y equals 1? Yeah. So, and you can even draw a nice dotted line there. There's the dotted line that represents y equals 1, the horizontal line y equals 1. And sure enough, the graph is approaching 1 to the right, and it's approaching 1 to the left. And how did we get to 1? By taking the ratio of the leading terms. The ratio of the leading terms will give you the horizontal asymptote. Provided, what if you do the ratio and it doesn't just all cancel out like that? Then you have to do something else. So add on to that, and then let x become, well, we say let x approach infinity. Let x become a very, very large number and see what you get. So, for example, what if you had the ratio 1 over 1x? Well, that ratio is just 1 over x. And as I now let x become a very, very, very large number, So just for fun, I always plug in a billion. What's 1 divided by a billion? Like 0.0000001, which is roughly 0. So in that case, the horizontal asymptote would be at 0, meaning the graph approaches the x-axis, and that would be your horizontal asymptote. We're going to do more examples of that one because that's a little particular. And in fact, we have to do a lot more talking about the horizontal asymptote. But the main idea I just wanted you to write down is that to find your horizontal asymptote, you take the ratio of the leading terms. And then there's more analysis that you have to do. So for instance, if the degree of the numerator is less than the degree of the denominator, so let's just say it's x to the 1 over x cubed, well then that simplifies down to 1 over x squared. And as I plug a very large number in for x, it becomes 0. And so your horizontal asymptote is the x-axis itself. Whereas if the degree of the numerator equals the degree of the denominator, so like maybe you have ax squared over ax squared, then, I'm sorry, ax squared would be x squared. Then the x squareds will cancel out, and you're just left with the ratio of the leading terms. And that is going to be your horizontal asymptote. Whereas if the degree of the numerator is bigger than the degree of the denominator, so let's say you had x to the 4th over x cubed, then that's something else entirely called a slant asymptote. I absolutely know that I'm not describing this fully right now. What I'm really saying is, hey, let's hold off on these horizontal asymptotes until we get to it. But I'm definitely telling you right up front that you find the horizontal asymptotes by taking the ratio of the leading terms and then looking at what you get. So just real quickly then, I'll show you one of each. So here's an example where we have, I'm going to do 2x squared plus 7x plus 12 all over 1x squared plus, say 5x plus 6. Go. And notice here, where's my horizontal asymptote? What am I approaching horizontally?
2.
2. And look at the ratio of my leading terms, 2x squared over 1x squared. 2 over 1 is 2. So that's pretty basic. Whatever I make that leading ratio, make that a 5. Oops, make that a 5 right there. Right there. There. Now where's my horizontal asymptote? At 5. I can verify that by just putting in a horizontal line. And there you see it. So yeah, whatever the ratio of the leading terms is, that is going to give you the horizontal ratio, or the horizontal asymptote. What if now I make the degree larger on the bottom? Automatically, it makes the horizontal asymptote approach 0. Just the x-axis itself. And yeah, that's what it'll always be. But what if I make the degree in the numerator bigger? Watch how fun this is. Oh, that's not a good example. I would have to change my x-axis to notice that. There we go. Now what I have is still not a good example. Let me give a good example. There. Now what I have here is a slant asymptote. Let me just draw in the line 6x. Look at this one. And I can make this a better window. Gosh, so much about a good graph is your window. There we go. Now do you see, this is a slant asymptote. The green function is approaching asymptotically a diagonal line instead of a horizontal line. And so we call that a slant asymptote. Notice we still have a vertical asymptote at 0, but we have a slant asymptote, meaning the asymptote is going sideways. All right? Okay. Let's wrap all that up. How do I analyze a rational function? I know we need to talk more about the horizontal asymptotes, and we will. So let's sum this up. What is the domain? Yeah, it's the exclusions from the denominator. So the domain is the exclusions from the denominator. Well, that's how you find it. Right? The domain is all real numbers except the exclusions from the denominator, but that's how you find it. You find the domain by looking at the denominator. Where are the holes? That's any factor that cancels. from the top and bottom. Where are the asymptotes? That's any factor remaining in the denominator. What is the y-intercept? Plug it in 0. What is the x-intercept? Set numerator equal to 0. And solve. Where are the vertical asymptotes? Set denominator equal to 0. And solve. And what are the horizontal asymptotes? Take the ratio of the leading terms. All right. So this, again, is like your cheat sheet. We now have to go off and actually do a whole bunch of these. You know, let's go practice, go look at a bunch of rational functions and analyze them. But we now have the definitions of everything that we're looking for. And you have the mental homework assignment to go home and think about why factors in the denominators create asymptotes and holes, specifically asymptotes. While we're at it, I think we can now make a really nice formula sheet as well, which I think is always a good idea. I can make, see, we started right there, but I think we can do better. Let's say we have f. Oh my, I now don't have any, oh, there's my black pens. We now have some function, which we're going to start off with something like this, right? They give us a polynomial, ax squared over bx squared. So we start with some sort of polynomial over a polynomial. And then our first job is to factor it. And once we do factor it, we can now analyze all of this and get all the information we want. So first of all, we know that our factors in the numerator are all x-intercepts. We know that our factors in the denominator are all vertical asymptotes. We know that anything that cancels is a hole. We know that plugging 0 in will give you the y-intercept. And we know that the ratio of the leading terms is the horizontal asymptote. I draw this all out because I think it's a fairly succinct, snappy way to visually tell you where to look for information. I also think that that would make for a really good face tattoo. Or maybe a back tattoo. You know, and let the world know who they're messing with. But at the very least, you know, that would be something good to write down over and over again until you have it memorized and burned into your brain. That's where you find all the information. Or you can write it down in a list, like that list. And that can remind you where to find all of your information. Totally up to you. But we're now ready to talk about rational functions. Oh boy, oh boy. So everybody, now take out chapter, did I give you chapter 4? It was back there, right? Okay, good. So taking a look at chapter 4, there is a 4.0. We don't have to do that page. Let me just look at it real quick. Yeah, we don't have to, because this is just practice factoring. Yeah, factoring and dividing. This was technically for another class. So you can skip all the way past that and open up to 4.1. You can skip all the way past that and go to 4.1. So on 4.1, you'll notice, as always, the packet gives you some definitions. We've already basically covered all the definitions. So we're going to move on ahead here. and go to the first example. Before we start, would anyone like to ask any questions? I try to sympathize and empathize with you all the time. I try to think, what are they experiencing? What's going on in their minds? How are they feeling? And I'm suddenly reminded of a quote by Winston Churchill. Winston Churchill, who was he anyway? The Prime Minister of England during World War II? Did I get that? Well, anyway, he has this funny quote about history. He says, history, one damn thing after another. And like that's how he kind of encapsulated like reading history books. Because when you read a history book, you're like, oh yeah, then that happened, and then that happened, and then that happened, and then that happened. And so I wonder if sometimes that's how you feel about math class. Like, all right, now rational functions. All right, now polynomials. All right, now this. And you know, it might just seem like a whole bunch of disjointed, like, okay, now we're learning about this function. Now we're learning about this function. But I really hope that you see the underlying commonality. What's the underlying commonality of all these things that we're studying? Certainly, solving correct. Yeah, the graph and the function and how the two relate to each other. So on the one hand, we have some function and it's something, you know, in terms of x, maybe it's, you know, something like this. So we've got some function. And then on the other hand, we've got some graph, right? And no matter what that function is and no matter what that graph is, what we're trying to do is understand the connection between the two. We're trying to understand, if you're given a function, how do you make the graph? If you're given a graph, how do you write down the function? How do you analyze the function to understand the parts that tell you about the graph? And if you're looking at a graph, how do you know which parts are important, like the x-intercepts, y-intercepts, asymptotes? They tell you how to build the function. So yeah, you know, we move along from one creature to the next creature to the next creature, but we're constantly asking, what's the relationship between function and graph? So I hope that that provides you like a big picture concept or a lens through which to view the study of mathematics. Okay, well, here we go, folks. In these examples, they're giving us quite a few things that they're looking for. So read through that list and look at all the questions they're asking. Just read it to yourself. It's a long list, isn't it? It's a tall order. So let's go through the list just once with one of these problems, but then we're just going to focus on certain parts. So for instance, we'll look at number 1. And it says f of x equals x over 3x minus 6. Now before we do anything, what should we do to that denominator? Well, we can't get x completely by itself, but we can, factor out. Okay. So again, your first job is always factor anything that you're given. You're given something, factor it, if you can. It's like a standing order. Okay, so it says A. Should we start by looking at the graph? Anyone curious? Should we look at the graph first? Yes, Mr. G, let's look at the graph. Okay, I think so too. So that's x over 3x minus 6. What do we have? We have a nice little graph. There's one little vertical asymptote at 2, and the horizontal asymptote approaches. I'm just going to take a wild guess here, although it's not at all a wild guess. And I'm going to say that the horizontal asymptote is at 1/3. Do you agree that it looks like it's approaching 1/3? It's getting closer and closer and closer over on the right, and it's getting closer and closer and closer over there on the left. So I'm going to say 1/3 is my horizontal asymptote. So there's our graph. We have a vertical asymptote at 2. We've got our horizontal asymptote at 1/3. That's what the graph looks like. Do we have an x-intercept? Yeah, we have an x-intercept and a y-intercept at 0. Okay, so those are our basic properties. Do you want to go ahead and sketch that? Go ahead and sketch that. Before we do any actual work, let's sketch it. So what you're going to do to make a sketch is you're going to say, okay, I have a vertical asymptote at 2. So you mark 2 and you put a dotted line. And then we have a horizontal asymptote at 1/3. So you sketch a line. We had a vertical asymptote. I'm sorry. We had a y-intercept and an x-intercept at that point right there. And so far, what I want you to notice is that's what we know. We know we have a vertical asymptote, we have a horizontal asymptote, we had a single x-intercept and a single y-intercept. And now what do? When we did polynomials, you went like that, right? And so now with rational functions, we basically draw in a sketch that preserves the asymptotic information. So I have a vertical asymptote here, comes down, got a horizontal asymptote, and then vertical asymptote coming up. I have to go through that point, and then a horizontal asymptote to the left. And that's what we sketch. What's the key thing? The key is that your graph, your swoopies, you want to call these swoopies, you can call them whatever you want. When you're drawing your swoopies, they should approach your asymptotes, and they should go through any x-intercepts and y-intercepts that you found. So well done, you just made your first rational function graph. So let's go through our analysis. Find the domain. The domain is all real numbers except those numbers that would cause you to divide by 0. So what number can't x be? 2. Which, as it turns out, is our asymptote. Right? By the way, the word asymptote, the P is silent, asymptote. But it's a whole lot more cool if you say asymptote. Asymptote. Like you show up at a party and you're like, hey guys, we're talking about asymptotes. And they'll be like, I see what you did there. Pronounce the P. So anyway, just throw that out there. Asymptote. Asymptote. Okay, part B. Identify any vertical asymptotes. We already did. The vert, as. Maybe we'd be better off at just saying VA. Vertical asymptote is at x equals 2. Remember the equation of a vertical line is x equals the x-intercept. The equation of a horizontal line is y equals the y-intercept. So our vertical asymptote is x equals 2. Let's see. Identify any holes in the graph. Do we have any holes? No holes. Why are there no holes? Yeah, we didn't cancel any of that. So no holes. D. Find any horizontal asymptote if it exists. In fact, a horizontal asymptote does exist. And how do we find it? We take the ratio of the leading terms. My ratio is x over 3x, which it's helpful to put that 1 on top. It's 1x over 3x. The x's cancel out, and 1/3. Therefore, our horizontal asymptote is y equals 1/3. Again, remember, the equation of a horizontal line is y equals the y-intercept, and the equation of a vertical line is x equals the x-intercept. So our ratio of leading terms gave us 1/3, therefore our horizontal asymptote is y equals 1/3. We're going to do that. Okay, find the slant asymptote if one exists. Well, there is no slant asymptote. You only have a slant asymptote if you take the ratio of leading terms and your degree is higher on top than on bottom. So just no, non-applicable. F, graph the function. Using a graphing utility. Oh, graphing utility. That sounds fancy. Graphing utility. And describe the behavior near the asymptotes. Okay, well, we already did that. We have our graph. We're done. Questions about that? Well, let's quickly look at number 2. And in number 2, let's go backwards. Let's analyze it first and then draw a graph. That'll be exciting. So number 2, we have f of x equals. Now, hey, can we factor that at all? But we can't factor out a 7, we can't factor out a 2, so they're just kind of there. But at the very least, write them in order. That's 7x plus 3 and negative 2x plus 5. Why do we write it in order? Yeah, because we're civilized. Right? We're civilized people. You always put polynomials in order from highest degree to lowest degree. And you don't want to mess up. So, what do we have then? A. What's the domain? Well, the domain is everything except for what would make the denominator equal 0. So you have to take your denominator and set it equal to 0. Or more specifically, take negative 2x plus 5 and set it not equal to 0. And then do the algebra, so negative 2x is not equal to negative 5. and x is not equal to 5/2, which is 2.5. So our domain exclusion so far is 2.5. And by the way, what is it? An asymptote or a hole?
It's an asymptote.
It's an asymptote because we didn't cancel out any terms. So it's got to be an asymptote. So part B, it says identify any, well, I'm just going to go ahead and write VA right there, vertical asymptote. But part B says the vertical asymptote, so the vertical asymptote is a vertical line, x equals 2.5. That's my vertical asymptote. Again, folks, very clear here. X equals 2.5 is an equation of a line. That's what I would type into Desmos. I'm not saying the solution to this problem is 2.5. There's a very subtle difference. Normally when we say x equals 3, we think, oh, that's the answer. X equals 3. That's the number I can plug in to make the equation true. That's not at all what we're saying right here. We're saying that's the equation of a vertical line. If I plug in 2.5 into this thing, that does not make the equation true. It makes the equation undefined. Right? So just by context, we know that's not listing a solution. That's listing an equation. Okay, part C. Identify any holes in the graph. Do we have any holes? No, because we didn't cancel anything out. How about part D? Find the horizontal asymptote. We'd have to take the ratio of the leading terms. So for the horizontal asymptote, we take our ratio, which is 7x over negative 2x. The x's cancel out, and we're left with negative 7/2, which is negative 3.5. And therefore, my horizontal asymptote is the horizontal line, y equals negative 3.5. So again, that's an equation of a line. Just like that's an equation of a line. Find the slant asymptote. There is no slant asymptote because the ratio of the leading terms, we already did the ratio test. It produced a horizontal asymptote, not a slant asymptote. Okay, so now what do we graph? Hey, it didn't even ask us for x-intercepts. What's the deal? It didn't even ask us for y-intercepts, did it?
That's sorry.
What?
It did ask us for one.
Yeah, it didn't. Okay, well, let's just do that ourselves. What would the x-intercept be? Wherever the numerator equals 0. So that would be 7x plus 3. So 7 equals 0. 7x equals negative 3. X equals negative 3/7. So on your graph, just put an x-intercept to the left. That's negative 3/7. That's one x-intercept. What's my y-intercept? I plug in 0. So if I plug in 0 for x, notice those terms go away, and that's all you have is 3/5. That's 0.6. So my y-intercept is at 0.6. That's right there. Okay, I've graphed now my x-intercepts and my y-intercepts. Let's do my vertical asymptote is at 2.5. So I come over here to 2.5, and I draw a dotted line. And then I have a horizontal asymptote at y equals negative 3.5. So I come down here to negative 3.5. And I draw that dotted line. So what do you think the graph looks like? Now that you have that basic information of your vertical asymptote, your horizontal asymptote, and those 2 points, what will our curve look like? Keep in mind, we're about to draw two swoopies. Two swoopies that, that have to match that information. So before you do anything, I would look at a graph. Right, like that is as far as I expect you to be able to go by hand. At that point, you would type it into your graphing calculator, and you would verify what this thing actually looks like. Okay, so I'm telling you right up front, you want your calculator handy. And what does our swoopy look like? Like that. So looking at your graph on your graphing calculator, you confirm what we just saw from over here, that yes, my swoopies there and there. And I confirmed it by looking at my graph, and it conforms exactly to what I thought from the x-intercept and the y-intercept, that I had a swoopy up there. And that's it. Does anyone have a better name than swoopy? That's the best one? I think so too. I've been using the word swoopy for a long time. All right, well, nice little introduction there. Got 5 minutes. So let's take a look here. We got that. Now that was 1 and 2. Where's the rest? Ah, there's 3. Yeah, let's do a slightly more sophisticated one before we go. Let's do number 3. And by the way, you can cross out number 4 completely. Just scribble it out with enthusiasm and glee. So for number 3, oh gosh, I'm so torn now. I'm so torn. Do we look at the graph first and give us that quick, immediate satisfaction? Or do we do the analysis first by hand and then check the graph to see if we're right? You know, both are okay approaches to life. The one has a little more surprise in it. You know, so what do you think? Not look at the graph first? Let's not look at the graph first. Let's see how we do. Is everyone on the edge of their seat? Ooh, on the edge of our seat. Let's find out. So number 3, we have this function, and what should we do with it first and foremost? Yeah, factor it and see what happens. So factor that thing, 1 multiplies to make 12, it adds to make 1. Is it x plus 4x minus 3? All right. Now that little x on top, let's do a little something to that to make it look like a factor. How do I make x look like a factor? Right, just to make it look legit. Anyone? Yeah, 2 inches. All right, so there we go. That's what our function looks like. So let's go ahead and begin our analysis. Part A, what's the domain? X had better not equal -4 or 3. And what are they? Asymptotes or holes? Yeah, they're both asymptotes. I'm going to write VA. Oops. I'm going to write VA, VA. Just to kind of tell myself ahead of time, I don't have any holes. I have 2 vertical asymptotes. Or B. Identify any vertical asymptotes. I just did. So the vertical asymptote, the equation of the line, therefore, the equation of the line is x equals -4, x equals 3. And you know what? At this point, I'm going to begin my graph. Because now I can start putting these things on my graph. So I have a vertical asymptote at -4. So I go da, 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 da. And I have a vertical asymptote at 3. So I go da, 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 da. And we already have this amazing feeling of progress. Oh, look at us go. We're moving along to the problem. We've got a graph started. Identify any holes in the graph. We didn't have any. No holes. Part D. Find the horizontal asymptote if it exists. So to do the horizontal asymptote, I know we just did all this really nice work of factoring that. We have to go back to the original expression and to take the leading terms. So I have x over x squared. That's my ratio. So for my horizontal asymptote, my ratio is x over x squared, which simplifies to 1 over x. Because one of the x's cancels out. Now, the rest of the definition said, make the ratio of leading terms and then let x become a very, very large number. So if I let x become a very, very large number, like 1 divided by 1 trillion, that's essentially 0.00000 is 0. So we're saying that our horizontal asymptote is 0. That means our graph is going to approach the x-axis. So my horizontal asymptote is y equals 0. Again, that's the equation of the line, y equals 0. So now I'm going to give myself a dotted line. I should use different colors. My horizontal asymptote now is the x-axis itself. Okay. My blue asymptote lines pop a little better. So my swoopies are approaching the x-axis, and they're approaching my vertical asymptotes. You're all having fun. It's fun. We're creating a graph. Oh, boy. All right. Find the slant asymptote. There is no slant asymptote. None. Because the horizontal ratio test, that is going to tell us what type of asymptote we have. The asymptote is a horizontal asymptote, not a slant asymptote. And then find the graph. So what does our graph look like? We've done a lot, but we still need to get the x-intercept and the y-intercept. So first of all, what's the y-intercept? Again, you might want to go back to the original function. If I plug in 0 everywhere for x, 0 up here, 0 there and there, what do we end up with? 0 over -12, right? 0 over -12. And 0 divided by -12 is 0. So my y-intercept is 0. We should just make a note about that somewhere. Part G, y-intercept is 0. X-intercept. So now you let the numerator equal 0. Remember, any factor in the numerator is an x-intercept, so the x-intercept is 0. And so that's it. All right, what on earth does this thing look like? Here again is where I say you have to do the rest by looking at a graph. You could find out where the swoopies are by doing a table of values. You could just throw in some numbers to the left of -4, put in a couple numbers in between -4 and 3, and put a couple numbers over here, do a table of values. That would give you some dots. And And then once you see some dots, then you would know how to draw in your swoopies. But I'm giving you full permission to just go to the graph, type in x divided by x squared plus x minus 12. And that is what our graph looks like. So how do we sketch it in? Like that. So we have my graph over here to the left, asymptote, asymptote. The one in the middle, asymptote's down through our x-intercept and down. And then the other one is up there. Now again, if you feel like I cheated by just looking at the graph, you're like, why didn't I just look at the graph in the first place? Again, I could have still known how to draw those swoopies by making a table of values. Because had I done a table of values, and I chose maybe a value over here like -5, and then maybe a few values in here like -3, -1, 1, and 2, and then choose a value over here like 4, then that would have given me a whole bunch of coordinates, which once I saw those dots, I would have known where to put my swoopies. Right, is that fair? Okay. Folks, really nice work today. So sad that we have to leave. Do you all want to just stay for another half hour? Just stay for another half hour, keep doing some rational functions? All right, now let's see. I have one paper pass back to Brandon. Please come up here, Brandon. Homework due, today's Wednesday. Nothing's due today. Yep, I have nothing else to tell you. Please email me. I've told you what I do, right, in my office. I just sit like this and wait. And if I wait too long, I start to cry, just waiting for people to show up and email me. I sit at home. My wife said, what are you doing? I'm like, checking my email. No one has emailed me. Okay? I'm making a pretty strong case for you to email me, but see, I don't want you sitting at home feeling lost and like, oh no, I'm not getting it. I want you to contact me.